Oh, there we go. All right. Welcome to what used to be Math 331 problem solving. It's now Math 331 asterisk today. So this is the 7th lecture. And what we're going to do today is we're going to do things a little bit out of order. We are going to play some games. New homework goes over there. And donuts and munchkins go in bellies. And I will give free admission. And guaranteed admission as well. I will pay tuition, everything, to anybody who beats me. Do I have a volunteer for somebody who wants to play me? Ready? Free tuition. Admissions trusts me. All right. I will keep that up for a little bit. So here's how the game works. There's lots of different rectangle games. And the way it works is the following. So we have some rectangle. And then on your turn, you do a horizontal or vertical line and break it up. And then the next person goes and breaks it up, and you continue until there are no moves left. Okay? If you are the last one to make a move, you win. Okay? So for instance, let's say on my opening move, I go down like this. So now, on your turn, you could do another vertical line going all the way down. You could do a horizontal line, but the horizontal line would have to stop here because there's a break. So really, as soon as I've done this, I now have it broken up like this. And when you're doing your horizontal move, you can't go beyond a break. You go from an edge, from an end, to a break. Okay? Hello, welcome.
Yay.
Oh, you brought me breakfast? Thank you.
I did.
And I've got munchkins for you, so. All right, so does everybody understand the game? You alternate turns. Whoever moves last wins. When you move, you have to go all the way from the top to the bottom or horizontally. Okay? And if you beat me, you get free tuition to Williams. Now, for those of you who have already accepted and chosen to go to Williams, it's too late.
What? You won't pay for
No.
grad school?
I will pay for grad school. Deal. If you go to grad school in a good field, like mathematics, economics, you actually get paid to go. And I remember some of my students were just shocked because their parents were in so much debt to send them to college. And I said, you know, they pay you. Really? So, who thinks they can beat me?
Is it the last person to go?
Last person who goes wins.
Who goes first?
So, who wants to play me? Do you want to go first or second?
Second.
Okay.
End the game in 1 turn.
I mean, yeah, am I allowed to?
All right. So you're going second?
Yeah.
All right. So I will go there.
I can go anywhere?
Anywhere you want.
Okay.
But you got to go from boundary to boundary.
Okay.
I've already gone there.
Yeah, he can go to the green line.
What?
Yeah, but that's not cutting it. You can't go there. So you could go here, 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 all the way down, or from here to there, here to there, here to there. So you got to move so people can see.
Okay.
Oh, crap. Most people don't realize that you're supposed to take the upper right corner.
I don't think he realized. Can we try and help? Can we,
Sure, you can try to help them.
Any ideas?
No, but I'd take the lower left.
I'll remember this.
To be the last one too.
Okay.
I don't want you saying anything else.
Anyone else? Let's see. Alright.
Because I got the bottom right now. I'll give you the upper left if I get the bottom right. That's fine. Now you're dead.
Oh, am I?
Yes.
Yes.
You go. I go. It's looking good for me. Does it really matter at this point? No. All right. Thank you for playing. We're looking forward to your tuition money. Anybody else want to play me? I'll even let you choose if you want to go first or second. Do you want to go first or second?
Am I guaranteed a 4x4 board?
If you want to go second, sure. If you want to go first, I will probably not give you a 4x4 board. So this is actually one of the easiest games to find a winning strategy to. The winning strategy is, well, it depends on the board, but essentially it's just play. So let's think about what's going on. Let's start off with, a simpler board, 3x3. So at time 0, how many pieces do I have? I have one piece. After the first move, no matter where the first move is, how many pieces do I have? Two. So no matter what it is, let's say I went all the way down there. So no matter where you move, after the first move, there's two pieces. Now, we do the second move. No matter where you go, what will happen after the second move? There'll be 3 pieces. So every time you move, you increase the number of pieces by 1. So this is called a monovariant. An invariant, it sounds like Three Amigos. An invariant is something that only takes on one value. It's invariant, it's fixed, it's constant. A monovariant is a quantity that can only move in one direction. Okay? It can get larger, it can get smaller, it can stay the same, but it can't be alternating between larger and smaller. It's either, at every moment in time, it's either the same value as before or larger, or at every moment in time, it's either the same value before or lower. So if I have a n by n board, how many moves do I need to finish? It'll be how many moves until the game is over? Yes. N times m minus 1. So if the board is even, if either n or m is even, it's going to be an odd number of moves. And whoever goes first will go first, third, fifth, seventh. If it's an odd board, if both sides are odd, then you'll have an even number of moves and whoever goes second. So the trick here, which several people started to notice, is I'm being nice, I'm letting you choose if you want to go first or second, but I'm not showing you what board we're playing on. So I've done this in lots of different elementary schools. I've done this both in Williamstown and Lanesboro. I am sadly not allowed to bring a chocolate bar and actually break it up because that violates school policy. It's Commonwealth, it's not local regulations. I'm on the school committee. If it was local regulations, we'd fix it. If I had known we were going to switch to this, I would have brought chocolate, but we've got the Munchkins, which is close enough. So in all of these games, the goal is to figure out what is the strategy. So for this, what's going on is there's a monovariant. There's a great strategy for that. What I want to do now is I want to shift to a different game where something strange can happen. I can prove player 1 has a winning strategy. What would you like to know if player 1 has a winning strategy? What it is. So for this game, it's very easy to explain how to win. Just keep moving. As long as you don't do an illegal move, if you have the right parity, you will always win. For the next game, we can only prove the existence of a winning strategy for play one without giving you any idea of how to get to it. Now, to me, this is very strange. If you think about things in math, there's a lot of theorems like this. There's the intermediate value theorem, or the mean value theorem. How many of you have not seen either intermediate or mean value theorem? Has everyone seen this in a calculus class? Okay, good. So what they tell you is there is a point C such that this happens. But they don't tell you where that point is. For a lot of things, we don't actually need to know where the point is. We just need to know that some such point exists. And that's enough. Great. If you're proving the fundamental theorem of calculus, mean value theorem is one of the key ingredients. So sometimes just knowing the existence is enough. All right, so here's the game. We call it the dots game. So you have a bunch of dots. And then I always forget if you win if you go first or second, but it's very easy to figure out which it is. So on your turn, you choose a dot, and you eat everything from that dot up and to the right. And you just remove those dots. And then the next person chooses a dot, and they'll remove everything that's left from that dot and to the right. Do you think whoever moves first wins or whoever moves last wins? Last. Why isn't whoever... Yeah. So it's going to be whoever moves last loses. I might have phrased this wrong. I'm sorry. Do you think you win the game if you're the last person to move? Or do you think you win the game if you're the last person to move? So who should win? The person who makes the last move or the person who doesn't make the last move? Who doesn't? Right. Because if you win by making the last move, where should player one go? Bottom left, and this game is boring. Right? This is not a hard game to answer. Okay. Sure. So it's got to be whoever moves last loses. So your goal is not to move last. I am not willing to play anybody for tuition to Williams on this game. I know that player one has a winning strategy. I do not know what that winning strategy is. So I thought I would show it to you. How many of you have ever seen this game before? Right. This is a phenomenal game. Let's break the proof up into two cases. Do you agree that if I give you any board, either player one or player two has to have a winning strategy for any fixed board? It might be some boards player one has the winning strategy, and for other boards player two has the winning strategy. But somebody has to have a winning strategy on a given board. Why is that true?
Because someone has to end.
Someone has to end. Can this game end in a tie? So we have a distinguished visitor, one of my colleagues from the stats side of the department, a chess aficionado. What is the problem with chess? Or one of the many problems with chess?
Well, in theory, it is solvable as well. Someone should be able to win, but we don't know which it is because the game tree is.
We don't necessarily know that somebody should be able to win.
It could force a draw.
It could possibly force a draw. Chess can end in a draw. There's several ways you could end in a draw. Both people could only have kings left, and then there's no way you can do anything. If there's a threefold repetition of configuration of the board, that's a draw. Again, it's unlikely that these things will happen. We believe that white probably has the winning strategy played optimally, but nobody knows. Have I talked to you guys about how good I am at chess?
Yeah.
I have. I thought I told you, didn't I? Yeah, I thought I mentioned this. Yes. For those of you who are visiting, I used to be really good at chess when I was younger, and in my prime, I could actually simultaneously play the two top chess people in the world and guarantee at least a draw on both boards.
You were playing black and white.
Yes, I was playing black on one board and white on the other. And the board in which I was black, I just waited for the person there to move, and then, okay, then that will be the move on the board where I am white. And then I look at the response there, and then that will be my response there. So on this game, we agree that for any configuration of the board, there's a finite number of there's a finite number of trees, go through them all. Because each game has to end, somebody has a winning strategy. So there's two possibilities for this board. player 1 has the winning strategy, or player 2 has the winning strategy? If player 1 has the winning strategy, have we shown that player 1 has the winning strategy? Yes. So we only have to analyze the case where player 1 does not have the winning strategy. Player 2 has the winning strategy. That means no matter what player 1 does for their opening move, player 2 can force a win. Any thoughts on where player 1 should move?
I would make a 3x3.
So one possibility is to try to make a 3x3. But now you're trying to play and trying to figure out what that winning strategy is. I just want a theoretical point. And this was a point that was actually mentioned in the previous rectangle game. There's a nice point that will help the analysis.
Corner?
Yeah, which corner?
They're all the same, aren't they?
Well, no, if you go here, you lose. Top right. So imagine player 1 goes there. Player 2 has a winning strategy, correct? We are assuming we're in the case where player 2 has the winning strategy for the sport. So there's got to be some point where if player 2 goes there, they win. Let's say it's this point here, because I like this point. Okay? So if player 2 goes there, they will win. Okay? What should player 1 have done on their first turn?
The thing that 2 did.
Yeah, the thing that 2 did. What we want to do is we want to switch the moves between player 1 and player 2. So if player 1 goes here, and then player 2 goes here and forces the win, player 1 could have just gone there on their opening move. And so this proves that player 1 has a winning strategy. But it doesn't give you an idea of how to find it. So last year I supervised a thesis. She's now studying law at Stanford. And the idea was to analyze a new game I created related to the Fibonacci numbers. And her main objective was to teach me how to beat my daughter in this game. She was able to prove that except when n equals 2, if you choose any other positive integer as your initial seed, player 2 always has the winning strategy. But it was a non-constructive proof. And so I was really torn as to what to do. I mean, she did solve the problem. She did determine who had the winning strategy. I wasn't clear enough in my instructions to her that I actually wanted to know how to beat my daughter. So for her thesis defense, I actually pulled my daughter out of school, and she played my daughter live as part of her thesis defense. My daughter Kayla got to go second, and she made a mistake, and she could have won the game, and she felt bad about this. Fortunately, we had a prospective student visiting later that day, and she beat him, and he's elected to go elsewhere. But if people want, I can show you the Fibonacci game. People want to see this? It's another example of a game where you have a winning strategy that's not explicit. So here's how it's going to work. I'm going to have a bunch of bins. Here's my 1 bin, my 2 bin, my 3 bin, my 5 bin, my 8 bin, and so on. So let's say you give me a number like 10. I'm going to start off with 10 on the 1 bin. So the Fibonacci numbers satisfy the following relations. Fn plus 1 is Fn plus Fn minus 1. And you can also have a splitting move. Twice Fn is Fn plus 1 plus Fn minus 2. So for instance, 10 is equal to 8 plus 2. So on your move, you can do one of two things. If you have 2 bins where they each have a Fibonacci number in it, where they each have a bean in it, you can take those 2 bins and move it down. Or if you ever have a thing that's doubled, you can split. We have to be a little bit careful because you have 2 1s often in the Fibonacci's, or the 1 and the 0. I'm going to just have 1, 1 here. There's really not much that can be done for the first move. I've got 10 in the 1 spot. What's the only thing I can do? Yeah, I've got to take 2 1s and make it into a 2. So does everyone agree that the only thing I can do now is I have an 8 here and a 1 here. I took 2 1s and I made it a 2. Notice 8 times 1 plus 1 times 2 is still going to be 10. Now I have 2 moves. I could take 2 1s and make another 2, or I could take a 1 and a 2 and make a 3. what would people like to do?
Was there a goal?
So the goal is to be the last one to move. So would you like to take 2 1s and make a 2? Or would you take a 1 and a 2 and make a 3? So we take a 1 and 2 and make a 3. So then I now have 7 over here, 0 here, and 1 over here. So I've done 2 moves so far. Now I only have one possible move. I've got to take 2 1s and make a 2. All right. Now, how many moves do I have? I can take 2 1s and make a 2. I can take a 1 and a 2 and make a 3, or I can take a 2 and a 3 and make a 5. Any preference? I'm sorry? Make a 3. So this becomes a 4, this becomes a 0, and now I have 2 3s. So I can either split the doubled 3, or I can take 2 1s and make a 2. Thoughts? I'm probably losing track of the moves. Was that the 4th move, or was that the 5th move? Okay. Split which? The 2 or the 3s? Okay. So if I split this, 2 3s is a 6, so I get a 5 and a 1. The only move I can do here now is I can take 2 1s and make a 2. I now have 2 possibilities. I can combine a 1 and a 2, or I can combine 2 1s. Any preference? Combine 2 1s. So that becomes a 1. This becomes a 2. I can split the 2, or I can combine a 2 and a 1. No, let's combine a 2 and a 1. I can't remember, did I mark that on that move yet? No, okay. So then I can combine the 3 and the 5 and win. So in this case, that was 9 moves. So whoever went first won in this time. So what that means is whoever played second actually made a mistake. It's actually not that bad. If you want, if you email me, I can send you the proof of this, that player 2 has a winning strategy. The only time they don't have a winning strategy is when you start off with the number 2, because there's only one move, combine the 2 1s and make a 2, and then the game's over. Player 2 never gets a chance to move. Other than that case, player 2 has a winning strategy. Now there's something really interesting over here. Have we talked about Zegendorf decompositions yet in this class? Okay, we've talked about Fibonacci numbers. So I will show you the most useless property of the Fibonacci numbers. It is a strange curiosity. Now, if you look over here, the game ended, and I never have 2 terms, 2 boxes that are both filled next to each other. Well, that makes sense, because if they were filled, I could have combined them. And I never have anything that was doubled. Well, that makes sense, because if it was doubled, I could split. It's not clear that every game will end. But it turns out every game will end, and will end in a decomposition like this, where each bin has at most 1 element, and you never have adjacent bins that are filled. So this is called the Zegendorf decomposition. I and my students are actually the world experts on these now. Every number can be written uniquely as a sum of non-adjacent Fibonacci's. If you write the Fibonacci numbers like this, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. I will give you the standard proof. This is the computer science greedy algorithm proof. Give me a reasonable number, not too small, not too large. 3? Too small.
17.
17? Let's be a little bit bigger than 17. 74, there you go. 74 is a good sized number. So the way the greedy algorithm, this makes up for earlier. So 74. I look at my list. Well, the next number after 55 is going to be 89. So the greedy algorithm says, look at the largest Fibonacci number less than equal to your number. And so I'll set this off as 55, and then what do I have to add to get to 74? Is it 19? So I've got 55. Now I look at 19. What's the largest Fibonacci number less than or equal to 19? 13. It can't be the number next to 55. Because if it was, I'd subtract off 55, then I'd subtract off 34. I could have subtracted off their sum. That would violate that this is the largest Fibonacci number less than or equal to my number. So I know whatever the next number is, it can't be adjacent. So in this case, it's 13. So I'll write 19 as 13 plus 6. Now I look at 6. What's the largest Fibonacci number? 5. So I get 5 plus 1, and I'm done. So with a little bit of work, you can make this rigorous and prove every number has a decomposition. With a little bit more work, you can prove every number has a unique decomposition. It turns out this is an equivalent definition of the Fibonacci's. If you've seen the Fibonacci's before, they're normally defined by fn plus 1 is fn plus fn minus 1. This is our go-to definition of the Fibonacci numbers. Here's another definition of the Fibonacci numbers. They are the unique sequence such that every positive integer can be written uniquely as a sum of non-adjacent terms. All right, so let's try to unwind that. I will erase this example. So, was this a homework problem?
Yeah.
Oh, yes.
CS256.
Oh, excellent.
I think. Actually, I think it was an exam problem.
Do you want to make sure this is not a take-home exam that's going on right now?
Well, it was Brent that teaches it.
Yeah. I'm just making sure before I do this that this is not an exam that you currently have and are doing as a take-home.
Right.
Good. Because otherwise I'd ask you for some money or something for the lecture to continue. So let's look at the sequence of numbers such that everything can be written uniquely as a sum of non-adjacent terms. We start off with 1. We have to add 2 to our list because I can't write 2 as just one number 1. Can I put 3? Can I write 3 as a sum of non-adjacent terms on my list? No. What about 4? Can I write 4 as a sum of non-adjacent terms on my list? Yeah, 3 plus 1. So when they ask you, what did you learn at Williams? Well, we learned that 3 plus 1 is 4. What about 5? No. So we have to add 5. Can we get 6?
Yes.
Yeah. 5 plus 1 is 6. Can we get 7?
Yes.
Yes. Can we get 8? No. So we have to add 8. We can get 9, 10, 11, 12, but not 13. So as a nice exercise, this is an equivalent definition of the Fibonacci numbers. They are the unique sequence such that everything can be written as a non-adjacent sum. It turns out there's a lot of stuff you can do, and a lot of my summer students at Williams have investigated and proven stuff about this. They've actually gotten to go to conferences. Sometimes the conferences are in New York City. Sometimes the conferences are in France. You got to take the students to where they are. So one of the things we love to do at Williams is provide opportunities to the undergrads. And the reason is we don't have grad students. We don't have postdocs. If we have anything, the only people who can get it are the students. And so I've had students working on problems like this after their freshman year. You don't need that much knowledge in terms of facts to start working on something like this. So these are the Zeckendorf decompositions. I promised a really stupid property of the Fibonacci numbers. What was the number we originally had? Was it 74?
Yep.
Yes.
And that was 55
13
plus 13 plus 5 plus 1. Right? I'm going to shift every Fibonacci number down by 1. So what Fibonacci number follows 55? I'm sorry, I'm shifting up. I want to shift. I want to shift up, not down. 89. What number follows 13? 21. What follows 5? And what follows 1?
2.
All right, what does this add up to? What are we getting?
130.
I got 130. That's 100, 110. No, 120. 120. Okay. Anybody know the relationship between 74 and 120? Okay, so I just want to see. Let's do it this way. So we start off at 74. Okay. Who here has ever driven a little bit over the speed limit?
Never.
Never? Okay. Have you ever traveled at 74 miles per hour? Or it could have been in one of the states where that's actually a legal speed.
Yeah.
Yeah. Do you know how many kilometers per hour 74 miles per hour is? 119.091.
That's weird.
It's the golden ratio. This is the worst possible application of Fibonacci numbers. Imagine you are traveling in Canada and you need to figure out, okay, the speed limit is this, how much is this, and how long will it take me to get to some place? Well, what you can do is you can write your number in its second of decomposition. If you want to go from miles to kilometers, you shift every index down. If you want to go from kilometers to miles, you shift every index up. And this will give a pretty good approximation. I mean, look, I'm getting 120, and the answer is 119.1, essentially. You know. Why does this work? So the golden mean is essentially the ratio between adjacent Fibonacci numbers and the limit. How many of you have not seen this? Okay. Okay. So the golden mean is 1 plus root 5 over 2. And so the nth Fibonacci number divided by the n minus first, if you take the limit as n goes to infinity, this converges to the golden mean. So the ratio between adjacent Fibonacci numbers as n gets very, very large converges to the golden mean, which is approximately 1.6, which is approximately the conversion factor between miles and kilometers. So the larger your numbers are, the more accurate this conversion is going to be. What if I gave you a number like 11? Let's see how well we do. What would the Zeckendorf decomposition of 11 be? It's 8 plus 3, right? When we shift 8, what do we get? 13. And when we shift 3, what do we get? 5. So we would then get 18. And then coming over here, if I put in 11, so 11 miles per hour is equal to approximately 17.7. Not bad. All right, let's do one more. Let's do 4 miles per hour. So I would write this as 3 plus 1. When I shift, 3 becomes 5, 1 becomes 2, and you get 7. So 4 miles should be about 6.43 kilometers. It's not terrible, but it's not great. What you could do to make this a little bit better is do 40. Shift 40. So if I did 40, that would be 34 plus 5 plus 1. Shift, and then calculate what 40 goes to, and then what do you do? Divide by 10.
You could do like 40 trillion.
Yes, absolutely. And so, you can decide whether or not it's child abuse or not, but, my son, my daughter, and a lot of their friends have learned Fibonacci numbers and properties like this. Yes?
Are there any special properties of if you keep shifting up that?
If you shift up, say, twice?
Yeah, if you do a sequence of this
Well, so if you shift up twice, you should basically be rescaling by about 1.6 squared. Because you'll be shifting by 2 indices.
Okay, gotcha.
So Again, this is just a fluke coming from, I think, the French Revolution in terms of, how we got, what a meter is. This is not a religion class. Almost surely there is no deep meaning to the fact that the golden mean is close to 1%. I have to be careful and say almost surely. That's mathematicians covering ourselves. It's possible that things have been set up ideally so that we do live in a world where relationships like this hold. I doubt it, but I cannot eliminate that possibility. There's a lot of fascinating properties of the golden mean. Again, this is one of the nice things about this class. There is no class that needs this as a prerequisite. We have complete freedom to do whatever we want. So I don't think we have enough time to do this fully, but as long as we're on the golden mean, we should at least say a few things about the golden mean. It is the most irrational of all irrational numbers. There is no number that is more irrational. So what does this mean? Well, if I have an irrational number, I can look at a sequence of fractions, a sequence of rationals trying to approximate it. If I wanted to approximate pi, somebody start yelling off digits of pi.
3.14, 5, 2, 6, 5, 3, 5, 8, 9.
I don't want to spend the whole class writing things. So if I look at this, this is going to be a decent approximation of pi. I'm going to get a lot of digits. But it's a very expensive approximation. So in computer science and mathematics, the way we would measure the cost of an approximation is how many digits. So I'm looking at 1, 2, 3, 4, 5, 6, 7, basically like 7 or 8 digit numbers to get 7 or 8 digits accuracy. So the question is, can you get a similar accuracy with significantly smaller numbers? And there's a lot of rational approximations to pi that are much better. And you can ask, if I give you a number, how do you find these good rational approximations? This leads to a beautiful subject called continued fractions. And you can ask, for a given number, how well can you approximate it? And you measure by the size of the denominator. And so if you take some number alpha, you might want to say alpha minus p over q. I want that to be, can I get it smaller than 1 over q squared? And it turns out if your number is irrational, you can always do this. And then the question is, can I do a little bit better than 1 over q squared for every irrational number? I believe it's Herbert's theorem, you can throw in like a square root of 5. And that's the best you can do. And there's one number where this is sharp. Anybody want to guess which number where this is sharp? Golden mean. Any other number you can actually do a little bit better. And by any other number, I mean any other number that's not a trivial cousin of the golden mean. If I add 5 to the golden mean, it's really not a big deal. I'm just changing my numerator by now plus 5 times q. So the golden mean is the hardest one to approximate. All right, so if you want, we've got about 10 minutes left. I can prove to you that every irrational number can be approximated this well, or we can do another math game. First loud voice wins. This is how life goes. Game. All right. Let's do zombie infection. We have not done zombie infection yet in this class, correct? Okay. So the way it works is we have a grid. 1, 2, 3, 4. 1, 2, 3, 4. And if you have 2 cells that are infected, they can infect other cells. So if you share 2 walls with infected cells, you become infected. Okay? You can't be infected diagonally, so for instance, if I'm like this cell is not infected, it doesn't share any walls. This cell is not infected, it only shares 1 wall. But these 2 cells would be infected because they share 2 walls. Okay? So the question is it possible to put enough zombies on an n by n board to ensure that everybody's infected? So for those of you who have not taken a class with me before, I like smart-ass answers. What's the easiest configuration you can think of where you get to choose which cells are infected that will guarantee that eventually everybody's infected? Kill all of them, right? Start off with everybody a zombie, and surprise, surprise, at some point in time, everybody will be a zombie. All right, this is not a great achievement. Yeah. That costs n squared zombies. That's a lot of zombies to purchase. Can you give me a slightly smaller cost?
Squared over 2.
All
N squared over
Okay, so how do you get n squared over 2?
by doing like a check.
Yeah, by doing a checkerboard. So if you do a checkerboard, you can go from n squared to n squared over 2. That's much better. You've just saved 50%. What you could have also done is you could say, well, just leave one cell uninfected. But yeah, this is a 50% improvement, but it still costs on the order of n squared. So you want to get a sense of how expensive are things. Order n squared is still expensive. Do you think you can get it linear? Right, so how would we do it linearly? Yes?
Diagonal line.
Yes. So if you just infect the main diagonal, I'll just do it on a 3x3 board. So if I start off with the main diagonal, then on the next cell, on the next day, these all get infected, and then on day 2, these get infected. And so you can just show that you could actually always do it. Now that's really good. Now we're down to square root. So the question is, what if you only have n minus 1 zombies on an n by n board? Is it possible to place the n minus 1 zombies in such a way that everybody's infected at some point in time? And we're not going to simulate this by actually getting zombies and putting them on campus and seeing what happens. We'll do this theoretically. How would you start attacking this problem? How would you start building intuition? Which should you look at first?
2x2 wood, 1 zombie.
Yeah, 2x2 with 1 zombie, or even the 1x1 board with 1 zombie. So, with a 1x1 board, I can't infect everybody. Okay. The 2x2 board, everything is completely symmetric. The virus, the zombies don't propagate. If I look at a 3x3 board, it's a little bit more work. But I'll leave it as an exercise that it will not infect everybody. That if you start off with just 2 zombies on a 3x3 board, there will be some squares that are safe. And then you can begin to look at how many squares are safe. What's the best you can do? This is similar to the chess problem we were looking at before. All right, since we are down to about 4 minutes or so, I'm going to jump to the solution rather than having you ponder. It uses a concept we introduced today. Does anybody remember the great concept we introduced earlier today?
Invariance.
Yeah, the monovariance. So what we want to do is we want to find a monovariant. And the monovariant is going to be the perimeter of zombies. All right. Let's imagine we have 2 cells that are infected, and the cell between them is not infected. And let's assume that the cell above this is not infected and the cell below this is not infected. If you look at the perimeter of the zombie infection, this and this are both parts of the zombie perimeter. And these are not part of the zombie perimeter. So in the next moment, when this cell becomes infected, we lose these 2 green walls as internal walls now, but we then gain the ones over there. So the perimeter of the infection doesn't change. If you look at all the other configurations where exactly 2 of your neighbors are infected, you see if only 2 neighbors are infected, the perimeter doesn't increase. Perimeter is constant. If you have all 4 that are infected, then initially all 4 walls are part of your perimeter. They become infected, so you lose all. So if you have 4 neighbors that are infected, then your perimeter goes down by 4. The only case that's left is, well, what if exactly 3 are infected? Well, if 3 are infected, you lose 3 walls, gain 1, perimeter goes down by 2. So we note the following. Perimeter at time n plus 1 equals perimeter at time n minus either 0, 2, or 4. So the perimeter is never increasing. If you infect n minus 1 on an n by n, what is the maximum possible perimeter? So what would be the maximum possible perimeter if you have n minus 1 things infected?
4 n minus
4n minus 1. But what's the perimeter of the whole board? The perimeter of the whole board is 4n. So if only n minus 1 are infected, then the maximum the perimeter could be is 4n minus 4. You can't have everybody infected. There's got to be at least one person that's safe. Let's make the result even better. So sometimes, I call these like the foot in the door result. So we've got the foot in the door. We know that there's at least one cell that's safe. Is it possible that there's only one cell that's safe? No. Why can't there just be one cell that's safe? Yeah, it'll be infected. All of its neighbors are infected. So we must know there are at least 2 cells that are safe. Could there be exactly 2 cells that are safe if it's a 12 by 12 board? No. So my question is, can you actually push this to get not just that there's one square that's safe, but that maybe there's an entire row or column, almost like there's a fire line. If you think of forest fires, sometimes the best way to fight fire is with fire. And you actually burn down a patch before the fire gets there, so it can't keep building. There's a great quote, we fought fire with fire, and well, your house burned down twice as fast. But for some other things, it's really good if you have that discontinuity and stop things. So my question for you is, can you prove that there has to be either an entire row or column? All right, so this is a good place to stop.